So, good afternoon students. Today we will start with the case of classical ideal gas as a discrete degree of freedom example of the Gibbs canonical ensemble. So, like I always do in this course, I choose examples having both continuous degrees of freedom and discrete degrees of freedom. So, in the case of Gibbs canonical ensemble, I am going to take the example of classical ideal gas where a microstate is basically specified as the set of values of positions and momentums of the gas particles in a volume which also depends on the microstate. So, this is a system where you allow volume to fluctuate in order to keep pressure constant. So, volume of a microstate is also a variable that keeps fluctuating in addition to the energy of the system. So, just recall that the fluctuating quantities in this system are basically the Hamiltonian. So, if you fix the volume, then you have to allow for energy exchange in order to keep the total temperature constant. Okay. So, T is constant. So, I have to allow for fluctuations in the Hamiltonian, but if Hamiltonian is fluctuating, I will have a fluctuation in the enthalpy of the system. So, the enthalpy is basically the energy of that microstate plus the pressure volume work that the system does in order to maintain constant pressure. So, this is one fluctuating quantity which is the enthalpy. I call it as the enthalpy of the microstate. Okay. And the second quantity is as I have said is the volume. Okay. So, I have to change the letter here. This is the microstate here is specified as mu. So, I am going to call it as the enthalpy of the muth state, and similarly we are denoting V mu as the volume of the muth microstate. So, both the enthalpy and the volume are fluctuating quantities. Okay. So, you can include in this discussion the so you can write down that the fluctuating quantities are energy and volume, and we have written down the relevant thermodynamic variables whose averages that we have calculated. Okay. So, we have calculated the average of the enthalpy and the average of the volume. So, this is nothing but the enthalpy of the microstate, and this is nothing but that volume of the microstate, and also call them as the instantaneous volume or the instantaneous enthalpy. Okay. Now, the ideal gas is in the canonical ensemble, Gibbs canonical ensemble, can be specified by a probability density function which has to give the probability of finding a microstate in the vicinity of mu, and that can be, that is given as P of mu, and you can write down this PDF as 1 upon, so you can just write it down as the Boltzmann factor into h to the power into Boltzmann factor, which is e to the power minus beta into the energy of the microstate. Okay. And to normalize this, I have to divide it by the partition function. Now, this is not yet a probability density function, because it does not have the dimensions of the phase space volume. So, I am going to divide it by n factorial, that takes case into account the fact that the particles are indistinguishable. So, there are exactly n factorial permutations that you can do on n particles, and if I do not divide by n factorial, I would be overestimating the number of states by precisely that factor. So, taking into account the indistinguishability, I have divided by n factorial, and as I was saying that I have to non dimensionalize it in order to I have to make the dimensions 1 upon phase space volume. So, I am going to divide it by a few more factors. So, one factor is the cell factor, that is the smallest volume you can have in the phase space, okay, with n particles, that is called as the cell factor. And in addition to this, I am also going to divide it by some volume scale. So, V naught here is some volume scale, and this is because my phase space now has the additional degree of freedom, which is the volume of a microstate. Okay. So, as you can see, my phase space is not just it is not just composed of particle coordinates and momenta. The phase space now involves information of the volume of the microstate also, the physical volume of the box. Okay. So, I am going to say that my phase space here so the overall degree of freedom is movement in phase space, which is due to the microstate and volume of the box. For a given value of mu. Okay. So, that is why I have to divide by a volume scale to non dimensionalize my partition function. So, now I can write down the partition function looking at this equation 1, I can directly write down my partition function as Z NPT. Okay. So, to understand the preceding argument that my phase space and the volume of the box together constitutes the overall scenario, is to visualize our system. So, at some instant the system is in a microstate mu. So, mu here is basically the set of coordinates that I have specified here. Okay. So, that is my mu, and corresponding volume of the system is V of mu, and the system is constantly exchanging energy in order to keep my temperature constant, and it is also exchanging volume. So, there is a constant amount of constant interaction of the system with the reservoir mechanically. So, there is a continuous mechanical interaction which is manifested in the exchange of volume, and that keeps my pressure constant. Okay. So, thermal interaction is necessary to keep temperature constant, and mechanical interaction is necessary to keep pressure constant. So, then the partition function of the system can be written as including all those prefactors needed for non-dimensionalizing my partition function upon n factorial for indistinguishability, h to the power 3 n is to as for the phase space volume, and I am going to divide it further by a volume scale, because there is going to be a integral over all the possible volumes my system can take. So, my system can take volumes from 0 to infinity. Okay. Do not be surprised with these limits, because both these volumes have a very low probability of occurrence, as shall be seen when I write down the Boltzmann factor. And so, this will be a volume integral, and then we have a phase space integral, where I will have a 6n dimensional phase space integral over all the momenta and positions. So, I have removed the vectorial signs because I have taken the sum over 3n. Okay. Okay, as you can see, now they are components already. Each particle has 3 components of momentum and 3 components of position. So, my summation is not over 1 to n, it is now directly written from 1 to 3 n. Okay. So, I will not write down d cube q and d cube p into the Boltzmann factor, which is e raised to minus beta, the Hamiltonian of the microstate. Now, the Hamiltonian of the microstate is nothing but summation over all momentas, because that is the only energy a system can have, it is an ideal gas. So, I am going to use some new symbol, let me use alpha, goes from 1 to 3n p alpha square by 2m plus p v. Okay. This v is the volume integral that we are going to perform. Okay. So, now you can write this as 1 upon h to the power 3 n into 1 upon n factorial into 1 upon some volume scale integral v going from 0 to infinity dv. Well, you can straight away see that the position integrals will give me v raised to n. Okay. So, position integrals are giving me v to the power n, and all the momentum integrals can be written as just integral d some P1 momentum degree of freedom of first particle into e raised to minus beta P1 square by 2m, where P1 will take the values from minus infinity to plus infinity, and the entire thing will be raised to the power 3n. This v raised to n has come because of the fact that I have written v raised to n as integral dq1 dq2 dq. So, I am going to write it as so it is better that I write it as just integral d cube q, where q belongs to the box whole to the power n. Okay. So, a single particles volume integral over d cube q1, d cube q2 and d cube q3, which is integral over d cube q, is just volume V, and there are n such integrals. So, this is just v raised to n. Okay. Right. So, there is one factor that I have missed here. Let me just write down that factor. I am going to write it here. I need some space here. So, let me just move everything on one side. And I am going to write it as e to the power minus beta p v. Okay. That is it. Fine. So, you can write this as 1 upon h to the power 3 n into 1 upon n factorial into 1 upon v 0 integral v goes from 0 to infinity dv v raised to n, and this Gaussian integral will simply give me square root of pi by a. So, it is giving me pi by a is already beta by 2 m, and so it will give me 3 n by 2 into e raised to minus beta p v. So, I can bring out the constants outside. So, what I will have is basically just 1 upon h to the power 3 n v 0 n factorial into 2 pi m upon beta raised to 3 n by 2 into volume integral v raised to n e raised to minus beta p v. So, the prefactor here can now be written as 1 upon h to the power 3 n. So, I am going to take h inside the parenthesis. I am going to write it as 1 upon n factorial into v 0. I am going to write as 2 pi m k b t upon h square to the power 3 n by 2. Okay. And if you notice that this is nothing but a Laplace transform of v to the power n, except for the fact that I have taken the s here of the transform as beta p. So, this is called as the Laplace transform of v to the power n, that we already know is the result of Laplace transform as n factorial over a to the power n plus 1. Now, a here is beta p Okay. So, the variable a or s that you take in the Laplace transform is actually, this is a function of beta p, is already beta p here. Okay. So, if you do not remember Laplace transforms, you can recall that if there is a function f of x, then its Laplace transform is nothing but integral 0 to infinity e raised to minus s x f of x dx, and because the definite integral in x, it is only a function of s. Okay. Now, our function was v raised to n. So, Laplace transform of v raised to n is we can define it as e raised to minus beta p into beta p v into v raised to n d of v. Okay. So, fine. So, if you want to find out its answer, it is nothing but you take v raised to n as the first function, because its successive derivatives will reduce the order. So, if I take v raised to n as the first function, you can I am just going to write down 2 steps and then it will be clear to you how to do it. So, it is like v raised to n e raised to minus beta p v divided by minus beta p, the limits 0 to infinity, minus integral derivative of the first into integration of second Okay. So, as you can see, the limits will give this 0 here, because at infinity e raised to minus beta p v will dominate and at 0 v raised to n will dominate. So, this goes to 0, what you have is just n upon beta p into Laplace transform of v raised to n minus 1. So, if you continue like this until you get Laplace transform of 1, which is s, so that would be just n factorial. So, next term would be n into n minus 1, and so this can be written as beta p the whole raised to n plus 1, okay, when you end. The last term here would be Laplace transform of 1, which is 1 upon beta p or 1 upon s. Anyway, so that is a short discussion of how you do a Laplace transform. So, I am going to write down the result here, which is 1 upon n factorial v 0, and look at this prefactor, it is already looking like a length scale to the power 3 n. So, I am going to write it as 1 upon our de Broglie wavelength, temperature dependent wavelength, okay, to the power 3 n into n factorial divided by beta p to the power n plus 1, okay, and you can knock off these two n's here now, n factorials. So, what you have is just 1 upon lambda to the power 3 n into 1 upon beta p to the power n plus 1. Now, this is your Gibbs canonical partition function. Okay. So, notice that we have defined our de Broglie length, okay, as upon square root of 2 pi m kBT, which as we discussed in the a few lectures ago indicates the onset of quantum mechanical effects provided you have a reference length scale that comes from density. So, if you have one length scale, I will call it as a density dependent length scale, which is some kind of n to the power minus 1 by 3. Then when you have the de Broglie wavelength far exceeding this density dependent length scale, then you basically have quantum mechanical effects. Which is basically the fact that your density is so large that your density dependent length scale becomes very small. A large density would mean the density dependent length scale or interparticle separation is very small, particles are very close to each other, which means our lambda n will be very small. And if you have low temperature, then our dB wavelength would be very large because it behaves as 1 upon square root T. It increases as inverse square root temperature. So, the quantum effects will arise in the limit of high density and low temperature. Low temperature will make my numerator large and high density will make my denominator small, which means the ratio will be much larger than 1. That is called as the quantum limit. And similarly, when you have this ratio much smaller than 1, you have classical effects or you have a classical limit. So, here you are talking about high temperature that will make your de Broglie wavelength very small because it will go as 1 upon square root T, and you will talk about low density. So, in the low density limit my denominator will be very large because my particles will be, the separation would be much larger, there would be interparticle separation would be very large. So, the ratio becomes smaller and becomes negligible. That is the onset of classical mechanics. So, the de Broglie wavelength that I have taken here is a very important length scale in that sense. Okay. So, I am going to call this as lambda n as the density scale. And let us proceed with our calculation. So, we stopped at the expression of the partition function. So, if I look at the partition function, it has basically all the information available to connect statistical mechanics to thermodynamics, which is actually the goal of this lecture. And we can start off by computing the Gibbs free energy. Okay. So, for the sake of convenience I am going to copy this expression because I am going to use it immediately. Here. So, I can which gives me which gives me the Gibbs free energy, that is minus 1 upon beta logarithm of the Gibbs canonical partition function, and that is nothing but minus kBT, and if you take the log of this, what you basically get here is So, I am going to take the logarithm of this. Minus 3n ln of lambda t minus n plus 1 ln of beta p. Okay. Fine. Now, I already know that my Gibbs free energy. So, let me call this as equation 2. From thermodynamics, I know that my Gibbs free energy is written as H minus Ts, where H is the thermodynamic enthalpy. Okay. So, you can write down the differential form of this as dH minus TdS minus S dt, and this can be written as if I know if I write down H as E plus PV. So, this is dE plus PdV plus VdP. This is nothing but my d of H, okay, minus TdS minus S dt. Okay. So, you can now write down from the first law of thermodynamics, you write down for dE plus PdV minus TdS. Okay. So, you can now write it as just mu dN, okay, plus VdP minus S dt. Because I have used the first law as TdS equals to PdV plus dE minus mu dN. Okay. So, then I can write down each of these quantities mu, v and s by invoking the appropriate derivatives. So, by invoking the appropriate derivatives, I can compute chemical potential as dG over dN at constant value of pressure and temperature. I can also invoke the derivative with respect to pressure to compute volume, but then I have to fix number of particles and temperature, and I can also compute entropy by invoking derivative with respect to temperature, but holding number of particles and pressure as constant. So, you can compute these three thermodynamic variables easily. I am going to compute only one and leave the others as homework. Okay. So, I am going to demonstrate how to compute one of them. So, let us compute volume. Okay. So, volume is derivative of free energy with respect to pressure holding n and T tight. So, let us look at the expression for the Gibbs free energy. So, if you hold temperature and pressure, temperature and number of particles constant, then I can see that the first term in the Gibbs free energy does not contribute to volume, because it depends only on number of particles and temperature. The de Broglie wavelength is purely a function of temperature. Now, the only term that contributes here is the second term, and at constant temperature and number of particles, I can write it as n plus 1 into k T into d over d p of ln beta p, okay, at constant n t. Fine. Now, you can see that I can take the beta outside, it does not depend on pressure. Okay. So, this can be very easily computed. So, you can write it as n plus 1 k b t, and the derivative of ln beta p is just 1 upon beta p into beta. You can knock off these betas and write down the final answer as just n k b t over p. This is because n is very large compared to 1. So, n plus 1 is the same as 1, n plus 1 is the same as n. Okay. You can write down that since this is the case. So, then this is the ideal gas law. Equation of state. Okay. All right. So, so now we have the equations for the chemical potential, volume and entropy, from which we have already computed the volume, and I have left the computation of the chemical potential and entropy as an exercise. So, I will just finish the entire calculation by computing enthalpy. So, the thermodynamic enthalpy. So, this is a task that is that can be done by saying that you can compute the average of the instantaneous enthalpy. So, you sum over all the microstates. So, this is a microstate mu with a volume V mu, and you take the enthalpy of this microstate, which is the Hamiltonian plus P V, and you have to sample it in the distribution of the microstates. Okay. And this is nothing but a summation over the entire microstates of so we are going to sample the enthalpy in this distribution. So, I am going to write down the distribution that we already know for our system. This is the energy scale. So, this is the partition function, that is sum over all the probabilities, and to pull out h plus p nu, I need to just derivate it with respect to beta just once. So, I am going to take a negative derivative with respect to beta of and just minus 1 upon z d by d beta of z, which is nothing but minus d by d beta of ln z. Okay. Now, we know that the partition function is given here. So, I am just going to copy the expression for the partition function. So, for just convenience, so what I have just obtained is basically the equation for my enthalpy. Okay. And if I recall that my partition function is given by this expression. So, I can compute ln of z as simply minus 3n ln of lambda t minus of n plus 1 ln of beta p, which means minus ln z will become plus on both the terms. And what is required here to compute the enthalpy, I am just going to substitute for in fact, I am going to just substitute for minus ln z. So, I can rewrite this as d over d beta of minus ln z, and for this minus ln z I am going to substitute this expression that we have just computed. So, I am going to substitute for this minus ln z this expression, okay. And this will make my enthalpy as d by d beta of thrice n ln lambda plus n plus 1 ln beta p, okay. And this can be very easily computed. So, 3n comes outside, what I get is basically 3n by ln of lambda t into the derivative of lambda t plus n plus 1, which is a constant, divided by beta p and into p. So, that completes the derivative. You can straight away knock off these two p's, and since our de Broglie wavelength was given as h upon square root of two pi m k b t, I can also write this as so just to save some space here, I can also write it as h into beta upon 2 pi m the whole square root. Okay. So, then this simply becomes 3n, and I am going to substitute the value of lambda here, which is h upon h into square root of beta into 2 pi m square root, and the derivative here simply becomes h upon 2 pi m the square root, and derivative of square root beta is just 1 upon 2 square root beta, plus the second term I am going to write it as n times 1 upon beta, because n plus 1 is equal to n, as n is very large. So, we are doing a thermodynamic, so it is all in the thermodynamic limit. So, if you knock off all the terms, that cancel, you are left with nothing but 3 by 2 n kBT plus n kBT, which is nothing but 5 by 2 n kBT. Now, this is your thermodynamic enthalpy. Therefore, you can compute the heat capacity at constant pressure as simply derivative of enthalpy with respect to temperature at constant pressure, and this is nothing but 5 by 2 n kBT, and this is larger than heat capacity at constant volume as it should be. This is because you have to understand that the energy scale in the problem is enthalpy. So, the right derivative to take is the derivative of enthalpy, not the total energy, and that gives us the heat capacity at constant pressure, because you have taken the pressure constant in this ensemble. So, this completes the discussion on the Gibbs Canonical Ensemble and the case study, the particular case study of the ideal Caspar gas, which is a system of with degrees of freedom that are continuous. In the next lecture, we will discuss a system which is a magnetic system of n spins, and we will continue from here and look at the thermodynamic properties of a magnetic system of n spins. Okay. So, we close the lecture here.